Hi, everyone. I'm Harlan Haskins, and I'm here to tell you about the awesome world of tools with libSyntax. So, to get started, I want to tell you a little bit about what we're going to learn today. So first, we're going to go over some compiler basics so everyone can get up to speed about the terminology that we're going to be using, and you hopefully won't have to Google during the presentation. Then I'm going to introduce libSyntax and go through some of its design choices and its APIs that are available. Then we're going to talk about how to write tools by writing a small Swift formatter using libSyntax. Great, so compilers. These are usually split into two pieces, one of which we call the front end and one that we call the back end. Each of these are pipelines that operate on your code. So first you'll start with the lexer, which takes your code and breaks it into a stream of tokens. Tokens are the littlest bit of syntactic information in the program. So in this case, we'll have 4 tokens. One of them, the struct keyword, the cat identifier, and the left and right braces. So then once we've broken down the code, we put it back together by passing it to the parser. The parser's job is to take that lexed set of tokens and turn it into a structured representation of the program. In this case, we're just going to have one node. We're going to call it cat. So then, once you've got a structured representation of the code, you pass it through various semantic analysis passes. Swift, at the beginning of semantic analysis, will do name binding, and it'll do a constraint solver and do all sorts of stuff to figure out your types, figure out your overloads, type check, make sure everything's OK, before passing it over to the back end. The back end tends to be a little more complex and involve some more steps. So you'll generate some sort of underlying code representation. Swift takes your code and turns it into a representation called SIL, S-I-L, Swift Intermediate Language. And from there, we run some more analysis passes over SIL. This is where things like definite initialization happens. Definite initialization is the pass over the compiler that makes sure that you've initialized all your variables, or that you've initialized all your properties when you're inside an initializer. So then you run it through the optimizer. And that optimizer is going to need to generate more code, which will be analyzed and re-optimized. And eventually, you get down into generating what's called LLVM intermediate representation. Now, LLVM is another lower representation of your source code between SIL and machine code. So LLVM will then run just a magnitude, hundreds of optimization, analysis, and verification passes before eventually lowering to machine code, which honestly itself warrants another forest. But eventually you settle on one binary file. To quote Scott Owens from the ICFP 2017, a compiler is just a big function that takes a string and returns a big int. So core to this whole thing is the Swift AST, the abstract syntax tree. It's the structured representation of your code that the parser produces. So here, let's look at this struct called cat. It has one property called name. That's a let. And if we look at a simplified version of the AST for this code, you'll see we have all the pieces represented-ish. We have the name cat. We have the one property name. That's a string. This is essentially what the Swift compiler thinks about when it reasons about your code. But notice that there are a lot of things missing. Specifically, what about all those, the colon, the spaces, the braces? All of those get thrown away when we do this very abstract representation. Well, we think that throwing this away gets rid of some important bits that we could use later. So the Swift compiler gained this new library called libSyntax. It's a new library in the Swift compiler that aims to represent the full contents of the source file and provides Swift and C++ APIs for reading files in, generating other Swift files, and analyzing them. And it works by keeping track of every one of those tokens in the tree itself, along with what we call trivia. Trivia are all the invisible bits of data, the spaces, the new lines, the comments, everything that normally gets thrown out at the beginning of parsing the code. The main goal is to be able to print the source file right back out from the structured representation. This is really powerful, and you'll see why. So let's look at a simple example of what libSyntax produces. This struct here will turn into this representation. Notice that all the tokens are still available in the tree. We have a tree structure, but the tokens are still there. Even more, this tree keeps track of the spaces after struct and cat. This design is crucial to one of libSyntax's main strong suits, syntactic transformation. So let's say we want to rename this struct from cat to feline. So recall how we parsed the tree. We have each token and the formatting and spaces around it. So if we want to rename it, we create a new identifier, feline. Well, what we've actually done by making this new identifier is we've created a completely different tree that represents a different source file. But if nodes haven't been changed, then they're shared with the old source file. That way we can avoid creating all new nodes and all new things. This also reinforces the notion that in libSyntax, the whole tree of your source code is only the sum of its parts. So you all may be wondering how all this stuff is structured under the hood. Well, libSyntax splits up the notion of the syntax tree into 3 constituent parts: raw syntax, SyntaxData, and the syntax nodes themselves. Let's go one by one. Raw syntax is the core of the syntax tree. It's structured as an enum with 2 cases. One of them is a node. A node is just an abstract idea for a piece of syntax that has children. So it has a kind that says what kind of node it is, if it's an if statement or a struct declaration. And it has an array of children, and then a presence. And that presence says whether or not that piece of syntax actually existed in the tree. This is important because libSyntax needs to be able to represent invalid or in-progress code. If you start writing a struct declaration but you haven't gotten to that last brace, we should still be able to recover from that and give you a tree that you can work with. So the other case is token, which represents a token. So it's got a kind that says what kind of token it is. It's got leading trivia that comes before it, trailing trivia, which comes after it, and also a presence. So you may be wondering about this trivia thing. When does a piece of trivia, like a space, belong before a token, and when does it belong after a token? Well, we came up with 2 specific rules for when certain trivia applies to certain tokens. So trailing trivia. Any token owns the trivia that comes after it up to the first new line, but not including it. And then every token owns the trivia before it, starting at the first new line up to it. This is a little abstract, so let's look at an example. Here's an empty if statement. So let's go token by token and figure out which trivia each piece owns. All right, so first we have the if token. Rule 1 says that it owns the trivia up to it until the first new line. After it up to the first new line. So it owns that one space after. But since we're rubbing up against the X token, we stop. And now we own all trivia via rule 2 before it from the first new line. So this if statement doesn't have any trivia before it, so it's good. It just has one space of trailing trivia. Next we move to the X. Same deal. One space after it, no trivia before it. We look at the equals. Same deal as the X, just one space after. We look at the 6. We might be seeing a pattern here. Most tokens in the tree are only going to have trailing trivia. The only time they're going to have leading trivia is if they come after a new line. So 6 has one space after it. Then we get into an interesting case. This brace has a new line directly after it. And rule 1 says it owns all the trivia after it up to that new line. So this thing has no leading or trailing trivia. But the brace after it has 2 new lines before it. So it is the owner of those 2 new lines. And it doesn't have any trailing trivia. So this is kind of how the libSyntax lexer is going to break up your code and assign trivia to each token that you can then mess around with when you're transforming the code. So next we'll talk about SyntaxData. It's a class that wraps a raw syntax node and then provides storage for the children. You can think of it as just a class that has an array inside. And that array, again, represents all the children of raw syntax, but the difference is that SyntaxData nodes have identity. A raw syntax node can be shared across multiple places, because a 1 in your source code is just a 1 that has a space or something after it. But the syntax data for a 1 in your source code is the specific 1 that shows up at line 7, column 4, or wherever else. Syntax data is also responsible for lazily creating its children, so that you only create nodes that you ask for and you avoid doing all sorts of other allocations. And finally, it points back to the parent so you can walk up the tree if you need to, and then visit neighboring nodes. Finally, the syntax nodes. The raw syntax and syntax data are hidden away completely. You'll be working with the syntax nodes directly when you're using the library. And there's a different declaration for each node in the Swift grammar, and these provide a type-safe way to get at each of the children. So whereas syntax data just has an array of all the children, if statement syntax is going to have an accessor for the if keyword token. It's going to have an accessor for all the statements inside. And then it also has functions for transforming the node and returning a new node with one of the children replaced. We'll talk about that in a little bit. So libSyntax gives you 3 APIs for creating syntax nodes. The MakeAPIs exist to create fully initialized nodes if you have all their constituent parts already. The WithAPIs exist to transform a node by replacing one of their children. And finally, the builders exist to let you incrementally build nodes as you determine what parts you need. So let's look at the MakeAPIs. Well, they're for making nodes when you have all their parts. They're all static methods on an enum called syntax factory, which serves to namespace them. There's one MakeAPI per node, and you have to provide all of the required children of each node you want to construct. So if we want to make this return 3 expression, then we create a return keyword. We create with 1 space of trailing trivia. Then we create the 3 expression. And then to make the actual return statement, we call makeReturnStatement, passing in that return keyword and the 3. And that gives us a fully syntactically valid return statement. So now the WithAPIs are what you use to transform nodes into other nodes. So let's say instead of returning 3, we want this struct to, or this statement to return hello. So we'll call this WithExpression method that says, I want, instead of the 3 expression, I want to make a string literal expression. And then we pass in the string literal. And what that'll do is it'll give us a brand new return statement that represents a completely different source tree. So finally, we have the builders. Now, for each piece of syntax, there's a corresponding builder struct. They provide an incremental approach to building syntax nodes. So if we want to build that cat struct from before, we only need 4 tokens. We need the struct keyword, the cat identifier, and the 2 braces. But structs have a lot more associated with them. They've got attributes, they've got generics, they've got inheritance clauses, they've got all sorts of other stuff, they've got members, but we don't care about almost any of those. So if we were to use a make API, we need to be upfront and say, yeah, so there's no generics, and there's also no attributes, and also there's no member. We shouldn't need to do that. So if we want to make this cat, first we'll make the struct keyword with 1 space of trailing trivia. We'll make the cat identifier with 1 space of trailing trivia. And then we'll call into the struct syntax builder initializer. This is an API that passes you in a closure a builder. And then you tell that builder each piece of syntax that you want to use. We only want to use these 4 tokens, so we could ignore all the other methods. We just tell the builder, hey, use this struct keyword, this name, and this left and right brace. All these APIs were developed under a set of guiding principles. Namely, you should always know what to do next if you're trying to build a piece of syntax. Notably, users of libSyntax shouldn't have to be Swift compiler experts. They shouldn't have to know that a struct declaration is called struct syntax. There should be a way for them to figure out those things. The APIs are flexible, and they'll always generate code that is structurally valid. Note that that doesn't mean that it's syntactically valid. If we were generating that cat struct, and we forgot the space of trivia after the struct keyword, then when we print it back out to a file, we'd have struct cat, which is not valid. So what's more, because the APIs are all named similarly, they're autocomplete friendly, which means you can just start typing syntaxfactory.make, and you can see a list of all the things that you want to be able to make. So now I'd like to give a little demo of writing a small Swift formatter using libSyntax. Right, so I've got an Xcode project here that just has a pretty simple small test case. And I'm writing an app called Bagel Finder because this is New York, and New York's got the best bagels. That's an empirical fact. I don't think anyone can agree with that, or that can disagree with that. But there are some things that people here can disagree with. I see some of you are cringing at the braces on a new line, and some of you are cringing at the spaces, and a lot of you are cringing at the semicolons. I don't like them either. So what I'm going to do is write a little formatter that puts those braces on a new line, or on the same line, gets rid of all those spaces between the equals, and removes all the semicolons that are unnecessary. So I'm going to just open up another file here and talk about this Swift format file. What we're going to do is import Swift syntax, so we have the parse APIs available for us. Then we're going to write a main function, and it's going to do the standard command line things. Parse arguments into a URL, and then ask libSyntax to parse that file for us. Then we're going to run 3 passes over those files. The first, or over the source file that comes out. The first is going to fix the braces. Each one of these passes takes a syntax node in and returns a syntax node out. So you can take the output of one of these passes and pass it as the input to another one. So first we'll run the fix braces pass, and then pass the output of that to the fix equals spacing pass. And then we'll pass the output of that into the remove semicolons pass. Once we're done with that, we will write it back to the original source file after we fixed it. So let's look at how to implement these passes. They're going to be subclasses of a class called syntax rewriter. And what syntax rewriter does is it goes through and visits all the nodes in your tree, and if you want to switch them out with anything, you just return a different node from the visitor. So we're going to override the visitor for visiting tokens. And if we want to fix braces, we'll say, OK, we'll switch over the kind of token. If we see a left brace, and that left brace has a leading new line, has leading new line is just a function that goes through the trivia and returns true if any of the pieces are new lines. If it has a leading new line, then we return a token, but with one space of leading trivia instead. Otherwise, we just return the token, unmodified. So that'll fix the braces. Then if we want to fix the spacing of the equals, let's remember our trivia rules. So for this equals, the spaces before it actually belong to the token before it, and the spaces after belong to the equal sign. So what we need to do is we need to modify both the equals token and a token that comes before an equals token. So what we'll do is let's open that up again. We'll ask the token's parent for the child at the next index. And then if that next token is a token and it is an equal sign, then we give the same token but with trailing trivia of 1 space, so that there's only 1 space before the equals. Otherwise, if the token we're dealing with now is an equals, we give the same token but with 1 space of trailing trivia. And if none of those were equals, then we just return the token unmodified again. So now removing semicolons. I'm going to ignore this for right now. And we look at the visitor again. We say, if we should remove the semicolon, then I'll just return a blank identifier token. That'll just get rid of the semicolon and give us something that's blank and will get erased when we write it out to a file. Otherwise, return the token itself. But should remove semicolon is an interesting thing that we need to know. So let's look at it. First, we check to see if the token that's passed in is actually a semicolon. And if it's not, then we return false, because we don't want to remove it. Then let's ask for the next token. If the next token doesn't have a new line before it, then it's 2 statements on 1 line, and we don't want to remove the semicolon because that would make the code invalid. So what we'll do is we'll say if the next token is a token, or if the next child is a token, then we return whether or not it has a leading new line. Otherwise, yes, we want to remove it. And that's it. That's the 3 passes. And if we go ahead and look back at this code so everyone sort of gets a feeling for how it's structured, and we run Swift format again, we'll watch it update this file in real time, and our formattings were just applied, and it's so much easier to read. Now, sorry about that. I would be remiss if I didn't explain that libSyntax is still heavily in development. The syntax trees that you get back from libSyntax are going to be very bare bones. They don't include all the structure. Mostly, they provide access to tokens with trivia, which is why all those formatting passes only really needed to deal with tokens. If that's all you need for your formatting right now, then you're good to start using libSyntax. Otherwise, you're going to see a lot of nodes called unknown syntax, and that's very unfortunate. To get that full structure, we need to go through and update the Swift parser to produce libSyntaxNodes. Or we can flesh out this legacy AST transformer that's currently in the Swift compiler. There's a lot of options that we can do, but we still need to do some work to get it to give us a good structure. So for more information about libSyntax and the Swift compiler in general, you can get to the libSyntax documentation by going to bit.ly/libsyntax, and you can get to the Swift open source repo at github.com/apple/swift. Thanks so much, everyone.